Okay, let's look at pages 2 and 3 of exam number 2 for fall of 2018 for General Chemistry 1. So question 4. Question 4 and 5 kind of go together, but we'll start with question 4 here. How many electrons are transferred in the following reaction? So if we're talking about reactions that transfer electrons, right, we're looking at a redox reaction. And to be able to identify redox reaction, we have to go through and look at our redox states or our redox charges. So I'm going to quickly go through and assign our redox states for our individual atoms in these reactions. Now, there's a list of rules to go through to assign redox states. Again, they're in your notes, they're in the book, they're in the slides. We went over them in class. These are just things that you guys have to know. But one of the most common problems I ran into is, remember that redox states are for each atom, okay? It's not an overall thing. I mean, yes, that's important overall, but we always assign it for each atom, okay? All right, so let's look at oxidation states. Copper by itself, that's copper in its elemental form. Anything in its elemental form has an oxidation state of 0, okay? Let's see if I can, I should be able to do it in blue. Oxygen's typically -2, right? Hydrogen's pretty much +1, always, right? We have a total of 6 minus from the oxygens, a +1, so nitrogen has to be +5. Got it. Copper here is +2 because it is bound to 2 nitrates, right? The oxygen here is -2, right? Nitrogen here is +5 still. Hydrogen here +1. Oxygen here -2. Oxygen here -2. Nitrogen here +4. Okay. All right. So we assigned oxidation states very quickly. I'm just going by the rules, right? Look at your rules, see if you can get to the same answers that I did. If you can't, then, take a pause, take a step back. I think I've got another video on where I kind of walk through in a little bit more detail. All right, so it asks how many electrons are transferred, so we have to find where there are changes in oxidation states. Well, copper goes from 0 to +2. Okay, so how many electrons are transferred? Well, it transfers 2 electrons, right? The copper loses, right? Copper loses 2, okay? And if copper loses 2, something has to gain 2 electrons. So let's see if we can find that. Well, right, hydrogen doesn't change. It goes from +1 to +1, right? Oxygen doesn't change. It goes from -2 to -2. Nitrogen goes from +5 to +4. Well, how many nitrogens go to +4? Well, 2 of them. So nitrogen starts out as +5 and 2 of them go to +4. So nitrogen goes from +5, right, to +4, 2 of them, so nitrogen gains 2 electrons. Right, so either one of those ways is valid for answering this question, right? We're just looking at what gains or what loses electron. By conservation of matter, conservation of energy, if something loses 2 electrons, something has to gain 2 electrons. If something gains 2 electrons, something has to lose 2 electrons. That's all it is. Okay, moving right along to question number 5. Here's phosphorus in its elemental form, right? Whenever something is by itself, right, it's its elemental form, so phosphorus here is 0. We could go through and quickly assign oxidation states. Oxygen -2. Chlorine here is +1. Hydrogen here is +1. Right, hydrogen here -2. Oops, oh, sorry, I got a little ahead of myself. Not -2. Oxygen's -2. Hydrogen's +1. Got it. Okay. Oxygen here -2. Hydrogen here +1. +5. Chlorine -1. Hydrogen +1. Okay. So we're asked to identify the oxidizing agent. Okay. So what is an oxidizing agent? Well, an oxidizing agent is something that causes oxidation to happen. Right? An oxidizing agent is an agent of oxidation. Right? It's something that causes oxidation to happen. If you cause remember, oxidation is a loss. Right? Oxidation is a loss. Right? It's a loss of electrons. If you cause oxidation, that means you cause something to lose electrons. If you cause something to lose electrons, that means you yourself have to gain electrons. So what is gaining electrons? Well, +1 to -1, right? The chlorine's gaining electrons. Reducing agents lose electrons. Oxidizing agents gain electrons. So 2 valid answers that I accepted here, right? The chlorine is the oxidizing agent. Right? Boy, I can't spell. All right, agent, or the HCl, right, is the oxidizing agent. Either one is just fine. Right? You have to know what an oxidizing agent does. Oxidizing agents cause oxidation. Oxidation is a loss, therefore oxidizing agents gain. And that's what makes these trickies. You know, agents are causing something to happen. All right. I'm not going to read through question 6 here. I'll assume you guys can pause and read through it. There's just some important things I'm going to highlight. The important part is where you have an unknown metal Q that reacts with chlorine and it makes QCl2. Okay. If something makes QCl2, right, that means the Q has to have a 2+ charge, right? The Q has a 2+ charge to balance out with 2 Cl1 minuses, right? That's just basically how it works, right? I guess I should elaborate on this, right? If I know that this is a metal, right? Metals are going to form cations, right? So technically it could be that, Q could have been fluorine and some other weird stuff, but I mean that's not going to be the case here, right? FCl2 is just not going to form. But anyway, we know that this is a metal, so Q has to have a positive charge. It balances out with 2 Cl minuses, so Q has to have a 2+. Okay. We know it's a metal, has to form a cation. That means its oxidation state or its ionic charge has to be 2+. And we know we have to have 2 Cl1 minuses. And the only metal here, right, which is going to have a 2+ charge exclusively, is going to be calcium. Now titanium can have a 2+ charge, so can vanadium and chromium, right? But I said in this question, which is, there's only one compound that forms. Right? So I was looking for some discussion about oxidation states and charges, and some discussion about how oxidation states have to balance out. And if we know that only one compound is formed, calcium is invariant in the sense that it will never have anything other than a 2+ charge unless it's in its elemental form. Question 7. We're given an amount of copper sulfate, or I should say copper 2 sulfate. It's dissolved into water, and we're asked for concentration. So this is straightforward, a molarity question, right? So we're starting out with 39.9 grams of copper sulfate. Molarity is moles per liter, so we have to convert this into moles. And the molecular weight of copper sulfate is 159.6. Again, if you don't know how to convert grams into moles, look back at my previous, right? So I converted grams into moles, and then to get the molarity, I divide moles by liters, right? So I converted milliliters into liters. And this is, I think it comes out to be like 0.9996 or something like that. So this comes out to be pretty much exactly a 1 molar solution of copper sulfate, if I do this math. Pretty straightforward, right? Molarity, right, capital M, equals moles per liter, right? So I convert to moles first in this step here, right? Convert to moles, and then I divide by liters, right? By doing this step right here to get my molarity. You can separate the red and the blue parts out, that's just fine. You can do the blue part first, that's just fine, right? You just have to get to moles divided by liters at some point, okay? Right, moving right along. Question 8. I'm not going to read it out to you again. I'll just highlight the important parts. We have a 6.34 gram sample of an unknown metal. We add some energy to it, and the temperature changes by that amount there. So we're given a mass, okay, 6.34 grams. We're given a Q, 186.06 joules. And we're given a delta T, right, of 32.5 degrees Kelvin. Now, technically it shouldn't be degrees there, it should just be Kelvin. Minor detail, so slight typo, sorry. All right, well, it's asked to find the identity of the metal, and there's a very subtle hint to the right, right? Subtle is very not true, right? I give you guys the heat capacities here and I say, hey, what's the identity of the metal, right? So we need to figure out what the identity of the metal is, right? The heat capacity. So we need to figure out C. Well, Q equals MC delta T, right? We have Q, we have M, and we have delta T. So we play the favorite game of plug and chug, right? We plug in some numbers. And we chug out an answer, right? And we can do this math and solve for C. So I got my C equal to 0.903 joules per gram Kelvin. Boy, oh boy, what a random number. Nope, just kidding. It's right there again. Right? So this is our buddy aluminum. Write out, take the important information out of the problem, right, and solve for C in this case. All right, last page. Right? We've got a Hess's law problem here. How can you tell it's Hess's law? Well, I'm asking you to calculate delta H, and then I give you, a variety of different let's call them ingredients to make one equation, right? So I give you a set of different reactions that have to add up to make that reaction there, right? That's what Hess's law is, right? We're calculating the enthalpy change, and we're given other reactions to do that, okay? So we need to figure out delta H. The way that I start these problems is I start to look for individual parts. Here's what I mean. I need to have P4O6 as a reagent, right? Something on the left of my arrow. Well, the only other place I find P4O6 is on the right, over here. So my first initial guess would be to multiply that by -1. If I do that by -1, I then can rewrite my equation by basically reversing the whole thing. Right? Okay. So I did that. I look for O2. Well, O2 exists in two different places. So if I see that, I can't really make a definitive statement yet about where I can get my O2 from. So I'm going to skip that for the moment. Right? I move on to P4O10. Here's P4O10 over here. P4O10 is on the right side of my arrow, and it's on the right side of my arrow here, so I'm going to assume that I don't have to do anything to my equation in green there. So I just bring it down directly. (2940.1 kilojoules). Okay. I mean, you can think of this as multiplying it by 1, right? We're bringing the exact same thing down. Okay, we've used everything we can, right? Now we just add up, right? I usually draw an arrow. I add up the stuff on the left side of my arrow, and I add up my stuff on the right side of the arrow. Okay, so P406 plus P4 plus 502. That's all on my left side. P4 plus 302 plus P4010. Okay. I'm just going to bring this closer together here. Okay. Now I just cancel things out. P4 cancels out with P4. O3 cancels out with 3 here, and we're left with 2. After I cancel out, I rewrite P406 plus 202 goes to make P4010. Last most important part, does this, right, are these the same thing? Yep, they look the same to me, right? Then we do actually the question, right? We actually answer the question, and then we have to add up our delta H's here. And I got it to be about negative 1300 kilojoules. I just add up my blue and my green values for delta H, and I get my value for delta H for the overall reaction. Okay, so brief summary. What I do is I start, right? If you look in blue, I found P406, I found P406. They're on opposite sides of the arrow, so I have to multiply by -1. And then I wrote out what happened there, right? I flipped my equation, and I made sure to change my sign, right? I made sure to change my sign there for delta H. I skipped over, let me do this in purple here, right? I skipped over O2 because I found it in 2 different places, right? It's not easy to tell which one I need to flip or swap or whatever it is. If I find something in 2 different places, I come back to it at the end. In green then, right, I found P4010. It's on the right side of the arrow. It's on the right side of the arrow, so I just brought it down directly. I added everything up, I canceled, and then I took care of my delta H's. Now, Hess's laws tend to be confusing at first, but if you convince yourself, and you don't need to convince yourself too much, I don't think, the answer for every Hess's law is already on the page, because you know that it has to add up to be equal to this. If you go through and you're multiplying or dividing or whatever you need to do, and your answer at the end does not match what's up there at the top, well, go back and just try it again, right? Go back and try it again until it matches up. Okay, and that's it. Let me see if I can zoom out here. If I can try and snag everything on the same. It's kind of a eye exam here, but hopefully you guys can see what you need to see. And that's the end of exam 2 for the fall semester of 2018 for Gen Chem 1.